and I put it into F, and I also put it into G. Actually, I'm going to do those separately. So I take X, put it into F, I get the output F of X. And if I take the same input and put it into the function G, we get the output G of X. So if after evaluating, I perform an operation, we'll just say addition, on the outputs of the two functions, I get the output of a new function called F plus G. So F plus G is the new function that's obtained by just adding the outputs of F and G. The important thing is that the input has to be the same for both. That's why we can say we have a single input that we're inputting into F plus G, because it's F evaluated for that input plus G evaluated for that same input. So this is just the name of the new function. And this represents the output of F plus G evaluated for an input of X. So in practice, this is basically what you would imagine, right? If I want to find F plus G, I just add F of X plus G of X. Note, like, this still isn't like multiplication. So when you see that F plus G of X, we're not in any way multiplying by X. We're just saying we're inputting the input X into the function F plus G. And that is equivalent to finding F of X and adding it to G of X. So F of X is just 1 over X. And then G of X is X minus 1. And we can think of that X minus 1 as X minus 1 over 1. So we have 1 over X plus X minus 1 over 1, and because there's subtraction there, we think of that as being in parentheses. What do I need to add fractions?
Common denominator?
Yeah, I need a common denominator, so since my denominators are X and 1, I'm going to get a common denominator of X just by multiplying by X over X here. And so we get 1 plus X squared minus X over X. And this is X squared minus X plus 1 all over X. And that can't be simplified. Like, we can't cancel those X's because the one in the numerator is involved in addition and subtraction, not multiplication, right? We'd only be able to cancel that X in the denominator if I could factor an X out of the numerator. So if I had a GCF of X in the entire numerator, then I could factor it out and cancel it. But because every term is not divisible by X, there's no way to cancel that X. Another way we can see it is if we were to, like, division is similar to multiplication in that, like, it distributes over addition and subtraction. So just like we can multiply a polynomial by multiplying by each term, we can divide as well by dividing, like, X squared by X minus X over X plus 1 over X. And that's a really good way to see how, like, we can't cancel anything unless we can cancel it from all three terms, because this one, we can't get rid of the X in the denominator, right? So, I mean, if we did this, we would just end up back where we started. But if as far as this and this go, like neither one of them is like a better answer than the other. It just depends on the context you're in. So like when we take derivatives, it's easier to take derivatives term by term than to take the derivative of a big fraction. So like that green one, which in this case is the same as what we started with, would be a more convenient form for it to be in if we were taking the derivative, whereas normally we would just leave it as a fraction because we can't cancel anything from the numerator and denominator. So sometimes seeing it like this as like 3 fractions makes it a little easier to see why we can't just cancel like that x there, right? That would be like not having this or this. Too many lines, okay. So let's look at f divided by g of x. Everybody cool with that one? Okay. So f divided by g of x is just f of x divided by g of x. And writing that first step is important. Just it's the kind of thing where like if everything else goes horribly wrong, like you get a point just for showing us that you understand conceptually what that means. I was kind of reminded as I was grading, like just of the importance of like writing everything out, because it's just so easy to make little mistakes, like just make really like silly mistakes that have nothing to do with whether or not you understand the concepts, just because you're stressed out taking a test. So the more you can write to help us understand that you know what you're doing, the more credit we can give you, right? So some of these like in between steps that sometimes might seem silly to write it down, but on tests that just gives us the opportunity to give you credit even if you make like a silly mistake that doesn't have anything to do with like understanding the concepts. Speaking of the tests, I finished grading my problems on our tests, which were the word problems on the front and back of the last page. And you guys did awesome. So well on those. I was really, really proud of you. I think every single one of you got the maximization problem right, I think. There might have been 2 people in all 3 classes that got it wrong. But, I mean, just like across the board, really, really good on those problems. Was that like the easy part or the hard part of the test? The hard part?
I thought it was all about the same.
Okay. I always like, if you guys do well on the part that you thought was hard, I'm always like super happy because I'm like, ooh, that means the rest of it's even better. Which I'm sure it is just as good. But I was super pleased with how you guys did on that last page. Okay, back to dividing. So f of x divided by g of x is 1 over x divided by x minus 1. And again, I'm going to think of this x minus 1 as x minus 1 over 1, just so we can think of it as dividing 2 fractions. So dividing by x minus 1 over 1 is the same as multiplying by what? Yeah, 1 over x minus 1. And again, because there's that subtraction, we put that in parentheses, and this ends up being 1 over x times x minus 1. A pattern that you might start noticing is that when you divide a fraction by like a whole number or something, anything that's not a fraction, that denominator just like kind of ends up in the denominator of the original fraction, right? Like, so if I have like 2/3 divided by x, that always just ends up being like 2 over 3x. So kind of the denominators like smushed together. Just like here, that x minus 1 just ended up in the denominator. So that's kind of, it's always true. And kind of a pattern that if you notice it can save you a little bit of work. The same is not true if the whole number is in the numerator. But if it's in the denominator, you can do it kind of quickly. Okay, so evaluating these with numerical inputs is the same idea. So if I have f minus g of 1, that's just f evaluated at 1 minus g evaluated at 1. So f of 1 is 12 divided by, make a straighter line than that, 2 times 1 plus 4 minus g of 1 is the square root of 1. So let's see, in the denominator, that's 6. So 12 divided by 6 is 2. Minus the square root of 1 is 1. So we get 1. Okay, you guys try D. I don't know why that's D. And then the A and B. So finish out this page. So example 3 is really similar to what we did in example 1. Just different functions. Okay, it looks like everybody's getting it. We have f of 4 times g of 4 was 12 divided by 2 times 4 plus 4 times the square root of 4. So that was 1 times 2, yeah? So that gives us 2. And then on 3a, the only thing to watch out for is your signs. So minus g of x. So we all got x over x plus 3 minus x minus 1 over x plus 3. But remember that because it's in a fraction, if there's addition or subtraction, these guys are in parentheses. And so this is x minus 1 over x plus 3. So we have to distribute that negative. So that negative sign applies to both terms. So we're going to get a positive 1 here over x plus 3. And then multiplying, we have f of x times g of x is x over x plus 3 times x minus 1 over x plus 3. And again, parentheses around the numerators and denominators that have addition or subtraction. And this is kind of interesting because it sort of shows like the difference between multiplying and adding and subtracting, right? So when we subtract two fractions with the same denominator, we keep our common denominator. When we're multiplying, we still have to multiply the denominators even if they're the same. So we're going to end up with x times x minus 1 over x plus 3 squared. So we have two factors of x plus 3 in our denominator. And that's what I thought I saw as I was walking around. Everybody seemed to get it. And you don't, on the right, you don't have to distribute at all because everything's already factored, right? The only time we have to distribute when working with these rational expressions is if there's addition or subtraction to do. So we have to get rid of parentheses in order to combine like terms. But over here, there's no addition or subtraction outside the parentheses, so we don't have to do any combining to simplify. Okay, let's have a look at tables and graphs. So again, same idea. If I want f plus g of negative 1, I'm finding f of negative 1 and adding that to g of negative 1. So in the table, I'll find the x value of 1 in the x column. F of negative 1 is going to be 5. And then g of negative 1 is going to be 4. And again, be sure, like, practice on your homework and then definitely on the test. Make sure you're writing all those steps out. I know these are fairly simple to do in your head, but it's also super easy to look at like the wrong line on a table, even if you know what you're doing. So that just gives us the opportunity to give you the credit because we know you're doing it right, even if you pop out like the wrong number in the end. So g minus f of 0, we're looking for g of 0 minus, I feel like I should be consistent with my colors, g of 0 minus f of 0. So g of 0 is 2. And f of 0 is -3. So we'll end up with 5. And then let's look at the graph, and then I'll have you guys finish both these up. So on the graph, it's the same idea. We're just getting those y values from the graph instead of from the table. So if I'm looking for f plus g of 4, then I want f of 4 plus g of 4. So remember, f of 4 is the y-coordinate of the point on the graph of f that has an x-coordinate of 4. So we find an x-coordinate of 4 on the graph of f that has a y value of 2. And then same thing with g. We're always looking at that same x value. So g of 4 is just down here at -2. So we end up with 0. Any questions on where we got each of those? Okay, so you guys go ahead and finish the last two on both of those.
I got 2 times 1 is 2.
2 times 1 is 2. Good. Jesse, what about f divided by g of 1?
0.
Good.
Oh, wait, no, wrong one. Yeah, undefined.
Undefined, right? So we get 6 over 0, which is undefined. The difference between 0 and undefined is kind of tricky, but there's a couple ways to think about it. Like, undefined is like when the question itself doesn't make sense. So if I ask, like, who's sitting in that chair, you guys would say nobody, right? That's like 0. Like, we have a chair, but nobody's in it. Whereas if I, like, pointed at the AC unit and I said, who's sitting in that chair? Like, that question just doesn't make sense, right? It's not that nobody's in the chair. It's that there isn't a chair to speak of. So another way you can look at it is, like, if you think of it in terms of multiplication. So if I have 6 divided by 0 and that was equal to some numerical value, if I cleared fractions, that would mean that 6 would be equal to 0 times a. But what is 0 times anything? It's 0, right? So that's saying 6 is equal to 0, which just can't ever be true. So that means there's no number that 6 divided by 0 can possibly be equal to. Whereas if I do 0 divided by 6, if that was equal to a number and I cleared fractions, I would get 0 equals 6 times a. And that can be true, right? As long as a is 0, that statement is true. And so 0 divided by 6 does have a numerical value. Also, remember when we find domains that we always say the denominator can't be 0, right? That's the only restriction on division or on fractions. So the same is true if we put numbers in. The denominator still can't be 0. Okay, where was I? Blue. What about f minus g of 0? Good. So 0 minus 2, -2. And then Anna, what about G over F of 2?
I got 0 divided by 0.5.
0 divided, was it maybe 1.5? Which is equal to? 0, yep. Right, 0 divided by anything is 0. Because if I have, I mean, it doesn't make a lot of sense to have 1.5 plates. But if you have 0 cookies and a bunch of plates, you just have a bunch of empty plates, right? There's 0 cookies on each plate. As opposed to the one above, where if you don't have any plates, you just have nothing to do with your cookies. You can't eat them, that's subtraction, not division. If you don't have any groups to divide them into, you can't talk about how many groups there are. Or how many are in each group, sorry. It's kind of like a pizza too. Like if I gave you a pizza and I asked you to like cut it into 0 pieces, like that's impossible, right? Because the pizza itself is 1 piece, and every time you cut it, you get more pieces. Like it's impossible to cut a pizza into 0 pieces, right? So we can't make 0 groups out of something. Okay, so let's talk interpretation. There's a little typo in example 5 that should say let f of t. I covered up my t, but this should be f of t. So when you interpret these, I think the simplest way to do it is to write the operation with each individual output described in words, and then you can look at that as a whole. So everything we talk about in this one is going to be in terms of t, so we'll make sure to put that in our final answer, but I'm not going to write it in each one individually. So I'm just going to kind of paraphrase here. So f of t divided by p of t. What does f of t represent? Yeah, the number of owls that are poached. And when we actually write our final answer, we'll be a little bit more specific, but this just gives us an idea of what we're actually doing the operation with. So then what does P of T represent? Yeah, the total number of owls. So what do you get if you divide the number of owls that are poached by the total number of owls? Yeah, it's like the percentage of owls that are poached, right? So a percentage or the ratio or the fraction of owls that are poached. So we're just looking at a portion of the whole. So this is going to be the percentage or ratio or fraction, however you want to write that, of spotted owls that in Oregon that are poached T years after 1990. And that T years after 1990 is important because we want to indicate that we're using the same input for both functions when we divide them, right? It wouldn't make much sense if we compared the number of owls poached in 1995 to the total number of owls in 2006, right? Like that wouldn't really give us much useful information. So the input has to be the same for both in order for this to make sense. So why don't you guys try number 6? So try writing those both out in words and ask yourself what you would get when you multiply them. Okay, Savannah, what does C of, oh, not T, yes, C of X represent?
Number of credits you take per year.
So number of credits. And then Colton, what about T of X?
That's the cost of tuition per credit taken per year.
Yes, good. So the cost per credit. So Megan, what do you get if you multiply the number of credits times the cost per credit?
And you get the cost of tuition for the credits.
Yeah, you get just like the total cost of tuition for that year, right? So the total cost of tuition in year X. Good. Okay, one more. So here, remember that, so we're given a revenue graph and then a cost graph, but remember, but then the questions are asked about profit. So remember the relationship between profit and revenue and cost is profit is equal to what? Yeah, revenue minus cost. So if I want to make a profit, Hannah, what can you tell me about revenue and cost if my profit is positive, if I make money?
Which would be on and the other. Would they be positive, like not negative? Or
So
would
when
they be
we
decreasing?
when we subtract them, we're going to get a positive number.
Yeah.
So how do they compare to each other? So if you make a profit, what can we say about revenue compared to cost?
Revenue has to be greater than the cost.
Sorry?
Revenue has to be greater than the cost.
Yeah, the revenue has to be higher, right? The amount of money that you make has to be more than the amount of money that you spend. And so if we have a positive profit, we're looking for places where the revenue is greater than the cost. So our revenue function, on R of X represents the Y value of our revenue function, right? The output of the function is the Y value. So when we say that revenue is greater than cost, we're saying on the graph that the revenue function is like literally above the cost function. So higher physically than the cost function. So if this is my revenue function, and this is my cost function, we're looking for places where the red line is above the green line. So where is that red line higher? Chloe, what do you think?
Wouldn't it be the point where they intersect enough? That you
Uh-huh.
start there?
Yeah, so this is like 125. And then so anything to the right of that, exactly. So more than 125 items. Good. And then Garrison, if we break even, what do we know about the cost and the revenue?
They're equal?
Yeah, they're the same, right? Because that's the only way to get 0 through subtraction is if you subtract two things that are the same. So revenue is equal to cost. And Peyton, where does that happen?
At the intersection.
Yeah, so we're looking for where the Y values are the same. So that's exactly the point where they intersect. So it's like 125 items. And then, Shalea, if we're losing money, what can you say about revenue and cost?
If it's less than, the revenue is less than
Yeah, that revenue is less than cost, right? If you're losing money, then the amount you're making is less than the amount that you're spending. So we're looking for where revenue is less than cost. So again, that's just where the graph, the revenue function, is lower than the graph of the cost function. Emily, where does that happen?
Less than 125.
Mm-hmm. So here's our cost function. Our revenue function is below it for less than 125 items. Good? Okay, so tonight